All right, welcome back. Today we are going to continue our discussion of acids and bases. In the previous video, we talked about the different definitions of Arrhenius acids and bases and Bronsted-Lowry acids and bases, and we talked about the characteristics and how to identify them. Today we are going to talk about the strength of acids and bases and something called conjugates. So when we're talking about the strength of an acid or base, strong versus weak, concentrated versus diluted, or strong, weak versus concentrated, diluted. These are two different kind of terms that we use. Now, because of the discussion of ionization, and the Bronsted-Lowry model gives a definition of the strength of acids and bases. It's one of the things that makes the Bronsted-Lowry model a little bit different, a little bit better, is we're talking simply about the ionization. We're going to define acids and bases' strength based off of their ionization. So the strength of an acid or a base is solely based on the amount of ionization that occurs when in aqueous solution. That's it. Its strength is simply about how much it ionizes. Okay, strong acids or bases are going to ionize completely, meaning every single molecule of that acid or base is going to separate into the ions that are going to produce the H plus or the OH minus. And so you're going to get complete and total ionization. Weak acids or bases will ionize partially, only somewhat, usually around 10%. So you're not going to get a complete every single molecule is going to ionize. You're going to get some of the molecules will ionize, but not all of them. And so there's not as many ions in solution. So the strength of an acid or base all has to do with the amount of ions in solution relative to the amount of particles. So strength has nothing to do with concentration. So how corrosive something is, or how the acid or base affects other things, has to do a lot with concentration, but that doesn't mean it's strong. You can use a weak acid or a base to do very corrosive things. So strength of an acid has nothing to do with its concentration. It's very important that you understand that strength is only about its ionization. So the strength is how completely it ionizes. It either ionizes completely or it doesn't. A strong acid ionizes completely, a weak acid does not. Concentration, as we talked about in the solutions videos, concentration is how much solute is dissolved. So you can have a whole lot of an acid dissolved, but not very much of that acid is going to ionize. It can still dissolve and not ionize. So strength is how much it ionizes, concentration is how much is dissolved. So let's look at some examples. Hydrochloric acid, or HCl, completely ionizes in water, and therefore, by definition, HCl is a strong acid. Now, hydrogen chloride, hydrochloric acid, when you dissolve in water, it has a maximum solubility limit, and its maximum concentration is 12 molar. That's the highest concentration you can get of hydrogen chloride dissolved in water, is 12 molar, 12 moles per liter. So 12 molar hydrochloric acid is both concentrated, because that's as much as you can dissolve in there, and strong, because it ionizes completely. However, if I were to dilute my 12 molar hydrochloric acid down to 0.1 molar, 0.1 molar hydrochloric acid is very diluted, but it is still a strong acid. And it's a strong acid because that 0.1 moles per liter are still going to ionize completely. The strength of an acid is all about whether or not it ionizes completely. Same thing with bases, all right? The principal component of vinegar is acetic acid, an acid that only ionizes partially. All right, so acetic acid is what makes vinegar vinegar. It's what gives it that lovely smell vinegar has. By definition, then, acetic acid is a weak acid. It does not ionize completely. It only ionizes partially. So acetic acid's maximum concentration is somewhere around 17 molar. That's the solubility limit of acetic acid at room temperature is about 17 molar. So 17 molar acetic acid is a very concentrated acid, and it's very corrosive and can do a lot of damage, but it's still a weak acid. And it's a weak acid because it does not ionize completely. It's very concentrated at 17 molar, but it is a very weak acid, or it is still a weak acid because it is not ionizing completely. Whereas 0.1 molar acetic acid is a weak acid that is also dilute because it does not have very much concentration. It has very little solute dissolved, and that solute does not ionize completely. It only partially ionizes. So a dilute, weak acid is going to have very few hydrogen ions. A strong dilute acid will have quite a few hydrogen ions because strong acids are going to ionize completely. Weak acids are only going to ionize partially. So strong acids bases ionize completely. That means the ionization equation is written with a single arrow to the right. So I have hydrogen chloride is a strong acid, and it's going to produce hydrogen ions and chlorine ions, and every single hydrogen chloride molecule is going to break apart into H plus and Cl minus, and so we have a single arrow to the right. Now, a weak acids or bases are going to completely, they do not completely ionize, and they're going to maintain a state of equilibrium. What that means is some of them are going to ionize, and there's going to be this constant back and forth where some of the molecules are going to come back together, and some of them are going to ionize. And so for every molecule you have that ionizes, you're going to have another molecule that goes back together. And so it reaches this point of equilibrium where there's only a certain amount that's ionized at any given moment. We call that equilibrium. And when a chemical process is in equilibrium, we draw its arrows both ways because it happens both ways. The hydrogen fluoride, the HF, is going to break apart into H plus and F minus, but then it is also going to have H plus and F minus that are coming together to form hydrogen fluoride. So it's going both ways. You've got the hydrogen fluoride breaking apart, and you've got the parts coming together, and that happens at the same time in equilibrium. And so that's why we draw a double arrow. So you can identify the equation of a strong acid or a weak acid or base based off the arrow. If it has a single arrow pointing to the right, then it's a strong acid or base. If it's a double arrow pointing left and right, both directions, then it is a weak acid or base. So acid strength is all about ionization. So let's talk about strong acids for a second. They completely ionize, which means they're going to produce a large number of ions in solution. And more ions in solution means electricity can be passed from one to the other, and therefore they conduct electricity, and you have an electrolytic solution. So strong acids are very electrolytic. They can conduct electricity quite well. Weak acids don't produce as much ions, and so they don't conduct electricity as well. Strong acids produce a lot of ions, so they conduct electricity quite well. That's why we use acids in batteries. Battery acid, because it conducts electricity quite well because they're strong acids. In fact, your car battery is sulfuric acid, which is a very strong acid. So we have these two different types of strong acids, monoprotic versus polyprotic. Some acids only have one hydrogen ion or atom in their formula, so when they ionize, they can only donate one hydrogen ion to the solution. We call these monoprotic because they only have one proton. Remember, a hydrogen ion is a proton. So they're monoprotic, meaning they have only one proton. Some acids have more than one hydrogen in their formula, and therefore, if they were to completely ionize, this doesn't always happen where they separate all of them. Sometimes only one of the hydrogens will come off and the other ones will stay on there. But if it were to completely ionize, you're going to have a whole lot more hydrogen ions in solution, but they have more than one hydrogen ion to give away, and so we call them polyprotic. Right? So you have poly meaning many protons. They have more than one. Specifically, if it only has two, we call it diprotic. So you have monoprotic and diprotic. Polyprotic would have more than two, but diprotic also fit the definition of polyprotic. So we're just going to use poly in this lesson video. So let's look at the example here. We have HNO3. This is nitric acid. It has only one hydrogen. And so when it ionizes, it's going to ionize and give you an H plus ion and an NO3 minus ion. So you're going to end up, for every nitric acid molecule, you're going to get two ions. You're going to get a hydrogen ion and a nitrate ion. And so it's going to create two acids in solution. Remember, you've got your cation and your anion. They're both ions. So if I ask for total number of ions, you have to look at both. But it's only one proton, and so it's a monoprotic acid. Whereas something like H3PO4, phosphoric acid, it has three hydrogens. So if it were to donate all three of those hydrogens, you're going to get 4 total ions in solution for every molecule of H3PO4. So you're going to get 3 hydrogen ions and 1 phosphate ion. And so that's 4 total ions from this compound. Now, both nitric and phosphoric acid are weak acids and do not ionize completely, so that's not necessarily going to happen, but I just want to give you the concept of how many ions could be produced for each of those molecules. So now let's talk about something called conjugates, because when acids are put in water, when you dissolve them, when bases are put in water and you dissolve them, they're either going to be a hydrogen ion donor or a hydrogen ion acceptor. So once it donates it, it is no longer able to donate a hydrogen anymore. So now it is something else. And so the Bronsted-Lowry model defines acids and bases based off of how they donate or accept protons. So once an acid donates that hydrogen ion, the species or the thing that is left is now capable of accepting a hydrogen ion and is now a base. So if I'm an acid and I give up a proton, once I give up that proton, I've donated my proton, I am now able to take a proton from something else. So if I'm an acid and I give up that proton, I am now able to accept one and I am now a base. We call that the conjugate base of the acid. So the acid gives up its proton and becomes a base because now it can accept a proton. Likewise, once a base accepts a proton, it now has a proton that it can donate, it can give away. And so if it accepts a proton, it is now capable of donating one, and so now it is therefore an acid. We call that the conjugate acid of the base. So every acid has a conjugate base, and every base has a conjugate acid. So how do we look at that? A conjugate acid-base pair are two chemical species whose chemical formula differ by one hydrogen atom. So let's look at some examples of that. NH3, or ammonia, and ammonium, NH4+. You'll notice that there's one extra hydrogen on the NH4, and so the NH3 is a base. It accepts a proton and becomes NH4 an acid. It can now donate a proton. So that's an acid-base conjugate pair because NH3 is a base that accepts one and becomes a acid that it can now donate. So we have H2SO4. When sulfuric acid donates one of its protons, it becomes HSO4 minus. And so now it has the ability to accept a hydrogen. All right, so there is a difference of one hydrogen there. This is your acid-base conjugate pair, where sulfuric acid is the acid and bisulfate is the conjugate base. Water and hydronium, H2O and H3O+. H2O is the base and H3O is the conjugate acid of that base. It can accept and donate that way. So when an acid or a base is dissolved in water and ionizes, they're going to be two conjugate pairs. So if I take an acid or base and I dissolve it in water, you're going to get two conjugate pairs because the water is part of this. All right, so you've got NH3 plus H2O are going to give you NH4 plus and OH minus. So in this instance, water is your acid because water is going to be donating a hydrogen. If you look at the whole reaction, you see that water is donating a hydrogen. So water is your acid, and therefore NH3 or ammonia is the base. Because if we notice, you look at the right side, you can see that the NH4 has accepted, or the NH3 has accepted a hydrogen to become NH4, and the H2O has donated a hydrogen to become OH. So if ammonia is a base, it's going to accept a hydrogen ion and become ammonium. And when it does that, ammonium is now an acid. It is the conjugate acid of NH3, that conjugate acid-base pair. So the base is NH3, ammonia is its conjugate acid. Whereas water is our acid, and therefore the hydroxide ion is our conjugate base. And so we are left with a conjugate acid, a conjugate base. So what you need to recognize, though, is that your acid and base are always going to be on the left side of your reaction like this, and your conjugate acid and your conjugate base are always going to be on the right side. So the acid and the base are the reactants, the conjugates are the products. So now we've talked about the strength and the concentration of acids and bases. Remember, strength is all about how much it ionizes. Concentration is about how much is dissolved. Strength has nothing to do with concentration. The strength of an acid is all about its ionization. And then these acid-base conjugate pairs. Very important that you recognize the difference between an acid, a base, and then their conjugates differ by only one hydrogen. Conjugate acid of a base is going to have one more hydrogen than the base, and a conjugate base of an acid is going to have one less hydrogen than the acid. I realize that's a little bit confusing, but if you look at it a few times, I'm sure you'll understand. I'm sure you'll get it. It's not super complicated. So, thanks for watching. Have a day.